Find the following for the given matrix A. Compute the characteristic polynomial, find the eigenvalues and corresponding eigenspaces, and then find the algebraic and geometric multiplicity for each eigenvalue. So part A is asking us to compute the characteristic polynomial. Now let's recall that if A is a triangular matrix, then by default, matrix A minus lambda times the identity matrix is also triangular. So looking at our given matrix A here, we can see that we're working with an upper triangular matrix, which implies that matrix A minus lambda times the identity matrix is also an upper triangular matrix. Now, since matrix A minus lambda times the identity matrix is a triangular matrix, then we know from our triangular matrix theorem that the determinant of A minus lambda times the identity is equal to the product of the entries along the main diagonal. So using this information, we are able to conclude that therefore the characteristic polynomial, or the determinant of matrix A minus lambda times that 3 by 3 identity matrix is equal to 1 minus lambda minus 4 minus lambda, 5 minus lambda. So this is the characteristic polynomial of matrix A. Now in part B, we are asked to find the eigenvalues and the corresponding eigenspaces. So our goal here is to solve the characteristic equation, the determinant of matrix A minus lambda times that 3 by 3 identity matrix equals 0 for all lambda. So setting the characteristic polynomial equal to 0, we have 1 minus lambda times negative 4 minus lambda times 5 minus lambda is equal to 0. And applying that zero factor property here, we have our three cases, leaving us with lambda is equal to 1. We have lambda is equal to negative 4, and we have lambda is equal to 5. So these are the eigenvalues of matrix A. Now, we also need to find their corresponding eigenspaces. So let's recall that to find an eigenspace, E sub lambda, we need to find the null space of the matrix A minus lambda times the identity matrix for all lambda. Now, since we have 3 eigenvalues, we're going to need 3 separate cases here. So let's go in numerical order. So case 1, when lambda equals negative 4. So we need to find the null space of the matrix A minus 4 times that 3 by 3 identity matrix. So we have our given matrix A is 1, 0, 0, 1, minus 4, 0, and then 0, 1, 5. And we are adding this to the 3 by 3 matrix, 4, 0, 0, 0, 4, 0, 0, 0, 4. So combining up those like terms, we are left with the 3 by 3 matrix going across the first row, 5, 1, 0, 0, 0, 1, 0, 0, 9. So now that we have this matrix, we're ready to find the null space. So in other words, we are going to row reduce the matrix A plus 4 times that 3 by 3 identity matrix, augmented with the 0 vector, to row reduced echelon form. So taking that 3 by 3 matrix we just found, we want to simplify this. So let's see. We could do a scalar multiple of 1/5 times the first row, and then we could use our second pivot position here to eliminate the entry below it by doing negative 9 times the second row plus the third row. So this is leaving us with a 3 by 3 matrix, 1, 1/5, 0, 0, 0, 1, 0, 0, 0. So we have attained that row-reduced echelon form, and we can see this is equivalent to saying that x sub 1 is equal to minus 1/5 times x sub 2. We can see that x sub 2 is a free variable here. And we can also see that x sub 3 is equal to 0. So we can now write the set of all non-trivial solutions to this system by saying that vector x, which we know is a vector in R3, is defined as the vector with components where x sub 1 is equal to negative 1/5 times x sub 2. X sub 2 is free, so it's just itself, and x sub 3 is equal to 0. So notice that we have a scalar multiple here of x sub 2. We can pull that bad boy out to the front, leaving us with x sub 2 times the vector minus 1/5, 1, 0. And while there's nothing wrong with this vector, notice it has a fraction. So we can remove this fraction by multiplying each component of this vector by the least common denominator, which is 5. So this is equivalent to saying x sub 2 multiplied by the vector with components, negative 1, 5, 0. And this is, of course, such that x sub 2 is a free variable. So using this general solution, we are ready to state a basis for the eigenspace. And we can say that the eigenspace E sub negative 4 is equal to the set of all scalar multiples of the vector negative 1, 5, 0. Or we can write this in the spanning set form, saying that this is the span of the vector negative 1, 5, 0. So I have used the form of this vector where we don't have the fraction, but keep in mind that if you have the vector defined with a fractional component, that's okay too. So now that we officially have a basis for the eigenspace E sub negative 4, we are ready to move on to case 2, when lambda is equal to 1. So we are looking for the null space of the matrix A minus 1 times that 3 by 3 identity matrix. So our given matrix A is 1, 0, 0, 1, minus 4, 0, 0, 1, 5. And we are adding this to the 3 by 3 matrix, negative 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1. So combining up those like terms across the first row, we are left with the matrix 0, 1, 0, 0, minus 5, 1, 0, 0, 4. So again, we now want to take this matrix and find the null space. So we are going to row reduce matrix A minus the 3 by 3 identity, augmented with the 0 vector, to its row reduced echelon form. So taking that matrix we just found, and starting with our first pivot position here, we can use this pivot to eliminate the entry below it by doing 5 times the first row plus the second row, which produces the matrix 0, 1, 0, 0, 0, 1, 0, 0, 4. And last but not least, we can take our second pivot position here and use it to eliminate the entry below it by doing minus 4 times the second row plus the third row, which produces the matrix 0, 1, 0, 0, 0, 1, 0, 0, 0. So we've attained that row-reduced echelon form, and we know that this is equivalent to the linear system where x sub 1 is free, where x sub 2 is equal to 0, and where x sub 3 is equal to 0. So writing the solution set for all non-trivial solutions, we can say that vector x is the vector in R3 defined as x sub 1, 0, 0. So in this case, we have that scalar multiple of x sub 1 that we can pull out to the front. So we have x sub 1 times the vector 1, 0, 0. And this is such that x sub 1 is free. So we can now use this set of all possible non-trivial solutions to define a basis for the eigenspace E sub 1. So we can say that this eigenspace is the set of all possible scalar multiples of this elementary vector 1, 0, 0, which is equivalent to saying we have the span of this vector 1, 0, 0. So this is the basis for the eigenspace E sub 1. And last but not least, we are officially ready for case 3, when lambda is equal to 5. So we need to find the null space of matrix A minus 5 times that 3 by 3 identity matrix. So we have our matrix A is 1, 0, 0, 1, minus 4, 0, and 0, 1, 5. And we are adding this to the 3 by 3 matrix, negative 5, 0, 0, 0, negative 5, 0, 0, 0, negative 5. And combining up those like terms across row 1, we have negative 4, 1, 0. We have 0, minus 9, 1, and 0, 0, 0. So in order to find the null space of this matrix, we need to row reduce matrix A minus 5 times the identity matrix, augmented with the 0 vector, to its row reduced echelon form. So taking the matrix we just found, we can simplify this matrix by dividing the first row by a scalar multiple of negative 1/4, which leaves us with 1 minus 1/4, 0, and multiplying the second row by a scalar multiple of negative 1/9, we are left with 0, 1, minus 1/9, 0, 0, 0. Beautiful! So taking our second pivot position here, we can use this to eliminate the entry above it by doing 1/4 times the second row plus the first row, which leaves us with the matrix 1, 0, minus 1/36, 0, 1, minus 1/9, 0, 0, 0. So we have attained that row-reduced echelon form, and we know that this is equivalent to the linear system, where x sub 1 is defined as 1 by 36 times x sub 3. We have that x sub 2 is defined as 1/9 times x sub 3, and we can see that x sub 3 is free. So we can use this linear system to define the set of all possible non-trivial solutions. So we have vector x is the vector in R3, where x sub 1 is defined as 1 over 36 times x sub 3. X sub 2 is defined as 1/9 times x sub 3, and then x sub 3 is free, so it's just itself. And we can factor that scalar multiple x sub 3 out to the front. So we have x sub 3 multiplied by the vector with components 1/36, 1/9, 1. And there's nothing wrong with this vector, but it has fractions. So in order to remove the fractions, we multiply each component by the least common denominator, 36, which leaves us with the vector 1, 4, 36. And this is such that x sub 3 is free. So therefore, we can say that the basis for the eigenspace E sub 5 is equal to the set of all scalar multiples of the vector 1, 4, 36, which is equivalent to saying that we have the span of the vector 1, 4, 36. So this is the basis for the eigenspace. So this completes part B, and we are now ready for part C, where we are being asked to find the algebraic and geometric multiplicity of each eigenvalue. So to do this, we recall that the characteristic polynomial is defined by the determinant of matrix A minus lambda times the identity matrix, which is equal to 1 minus lambda times negative 4 minus lambda times 5 minus lambda. Now, let's make some observations here about these factors and the basis for each eigenspace. We can see from our characteristic polynomial that each factor appears once in the characteristic polynomial. From the basis for each eigenspace, E sub lambda, we know that this basis contains one vector. So in other words, the dimension of each eigenspace is equal to 1. So therefore, we're able to conclude that each eigenvalue has an algebraic multiplicity of 1, because each factor appears once. And we can also conclude that each eigenvalue has a geometric multiplicity of 1, because the dimension of the corresponding eigenspace is 1. So this is our beautiful final answer to part C and completes the solution to this example.